Hello Nullcon, welcome to my session. Namaste, I'm ORM, a vulnerability researcher at CyberArk Labs. Thank you for having me and thank you for coming. We'll start with a question. What would you think if I told you that your identity could be held by your system admin? That's trivial, right? But what if I told you that your identity could be mine or any user on your identity provider? By the end of this session, you will find out how. In this session, I'm sharing not only success stories, but also rabbit-holes and failures. You may ask why? Because these are great learning opportunities. We'll start with a GET request. So, who am I? I'm ORM, a father, engineer, researcher, and a gamer. 8 years ago, I transitioned from engineering to research, and today I'm a vulnerability researcher at CyberArk Labs. My team's main focus on open source and identity-related systems. We share our work internally to make our products more secure, and externally via blog posts to give back to the security community. Our main agenda, today I will cover 2 open source identity providers research we did, Keycloak and Authentik. Each part will start with a technical background to set a common ground for everyone, and then a dive into a technique or a vulnerability. I will also share short demos exploiting the vulnerabilities we found. Part 1, Keycloak and web race conditions. We'll start with the technical background. What is an identity provider? An identity provider is a system that manages digital identities. In our case, users. The IdP manages users from users creation to login pages and password policies. It makes the developer's life easier. By integrating with an IdP, you don't need to manage users, store the password, and enforce expiry and all of that. The IdP manages it for you. Multithreading. Multithreading is a programming concept that allows multiple tasks or threads to be run on a single process. In the web context, web servers use multithreading to handle multiple requests concurrently. Web race conditions. Let's define the problem. Web servers processes requests concurrently, so multiple threads interacting with the same data at the same time can cause unintended behavior in the application. Limit overrun race conditions, the most well-known type of web race conditions. It enables you to exceed some kind of limit imposed by the business logic of the application. Examples will be redeeming a gift card multiple times, or withdrawing or transferring over your balance. Let's start with an example logic. This is our example logic. A request arrives with a discount code, the code is verified, and since it's not used yet, it will be accepted, and we will apply the discount. And we will set the variable to use. Then later, a second request arrives with the same discount code. This time, this code is verified, and since it's already used, it will be rejected and an error will be returned. From a timeline view, the first request arrives, accepted, then the second request arrives, and rejected. This is the expected behavior. Let's look at the race flow. In the race flow, both of the requests arrive at the same time, and because of concurrency, they are processed at the same time. In this time window, the code variable is not set yet, so both of the requests are accepted and are handled as if the code is not used. The time between the check and the update is called the race window. So, how can we test remote servers for web race conditions? The single packet attack. The single packet attack is a technique developed by Portswigger that allows encapsulating or packaging multiple requests in a single TCP packet. Generally speaking, the algorithm collects all of the relevant requests, sends most of the data without the last bytes, waits a few milliseconds, and then sends the last bytes of each request. The single packet attack algorithm, I don't care, show me how. To use the single packet attack, there are a few tools we can use. Burp repeater, turbo intruder, and more. Today we will cover the first option, using burp repeater. We start by sending the relevant requests to burp repeater, then edit each request. Within the repeater, we create a new tab group. Then we select the relevant requests. These groups are requests to be sent together. Then in the arrow near the save button, we can set the option to send the group in parallel, single packet attack. And that's it. Now you can test web applications for race conditions. Single packet, many requests on a single packet. Come on, they didn't fit from my understanding. From what I know, HTTP version 1 sends the data in the same stream. So if we send multiple requests in the same stream, they will just get mixed, and the server won't be able to pass it. Then I was thinking to myself, it would be cool to inspect the traffic in Wireshark. Not so fast. The single packet attack is an HTTP version 2 only mechanism. HTTP version 2 uses TLS. Okay, so let's decrypt. This took us into a journey, and in the end, we found this tool. Using this tool, we could extract the TLS secrets for decryption. So we have the secrets. Let's inspect some packets. We'll start with an HTTP version 1 traffic. In HTTP version 1, the data is transferred in clear text. The context of the messages is ASCII encoded on the wire. As can be seen in the image, the literal characters GET are sent on the wire ASCII encoded. In HTTP version 2, messages are called frames. The data is transferred in binary. As can be seen in the image, after decryption, the getRequest method is translated to the X value 82. In HTTP version 2, a new feature is introduced called multiplexing. Each frame has stream ID. These IDs represent channels, which can distinguish different messages sent. This feature also allows sending multiple frames on the same packet. So let's inspect the single packet attack. Here we can see the single packet attack is used to send 3 different GET requests in one packet. So HTTP takeaways. HTTP version 2 is binary and using streams. Using streams permit multiple requests and responses to be sent simultaneously. This feature also allows the single packet attack to work. Evaluation on Keycloak. Let's evaluate our learned methods on Keycloak. Our first target, Keycloak, is an open source identity provider maintained by Red Hat. It's the upstream of the Red Hat single sign-on. Let's dive into our first story. Everything is multi-step. Here, our journey started by inspecting the Keycloak database. We found that the users table is separated from the required actions table. As can be seen in the image, the verify email flag is maintained in a separate table. This means that no email verification is needed on creation. So we speculated, can we gain unauthorized access? This means that if we make a single packet with the registration and the login at the same time, we could log in without email verification. Let's inspect the code creation code. User creation code. As can be seen in the snippet, first a user is created, then later in the code we can see that the required actions table is updated. This is our race window. So if we time it right, we can register with an arbitrary and hopefully an admin email and log into the system. Let's race against user creation. This test required us to create some burp macros which allowed us to create user and login request at the same packet. We work with the debugger, stopping at the relevant code, then check the database status directly with no success. We failed. We lost the race against user creation. We lost the race, but this seems like a great opportunity to understand why, and more importantly, to understand how can we avoid race conditions. So, using debugger breakpoints and activating ORM logs, we found the missing piece. In the logs, we see the following 4 key items: auto-commit disabled, insert into users table, insert into required actions table, commit. Auto-commit disabled means that the application is using transactions. Transactions means the database is updated in one shot or not. So in this case, transactions prevented us from gaining unauthorized access. With race condition, everything is multi-step. Well, sometimes. But now we know how to properly find and avoid race conditions. Let's move to our first demo. We'll start with some background for the demo. In Keycloak, an admin can create an API key for developers to use on the system. On creation, the admin can limit the number of clients that can be created by this API token. In our case, we set it to 2. A developer uses this token while creating the clients via the Keycloak API. After using the API key, the remaining count is updated. Let's look at the demo. So we start by creating a realm, which is like a tenant. Then we create an access token and set the limit to 2. We copy this token and give it to the developer. The developer using this token, requesting to create one client, and also transfer this request through his bare proxy. We will check that the client was created. It was client 1000 and it's created. Now we'll take the user creation API request and we'll send it to the repeater. Now we will modify each request and we'll create more. In this case, we chose to create 4 different clients. Now we group them together and just give the group a name. We select the option Send Group in Parallel and we send it. Now let's look at the clients. And we've created 5 clients. And also, we have a negative number in the response, in the remaining count. Okay. So, in case you missed it, we were able to create 5 different clients using a token limited to create only 2. To summarize this part, we reported this issue to Keycloak security team. They confirmed it, made it public, and fixed it. Okay, that's it for this part. If you are interested in learning more about this research, you can check out our Keycloak blog post. You can't always win racing the Keycloak. In the blog, I cover these race conditions and more. Okay, let's dive into our next part, Authentik, Research, and ORM Leaks. In this part, we'll start with short technical background, then I dive into vulnerabilities we found in Authentik. Let's get started. Object Relational Mappers. ORMs are a programming technique used to convert data between relational databases and object-oriented programming languages. They allow you to manage data without using SQL queries. In ORMs, models define the structure of stored data. In the image we can see an example of a model created with Django, a Python framework that includes an ORM. Our new target, Authentik, is an open source identity provider maintained by Go Authentik.io. Authentik is a Django project. We'll dive into our first Authentik vulnerability, sensitive information leak. We'll start with some background for this part. In Authentik, certificates can be used for 2 main functions. The certificate that is attached to the HTTPS server, the Authentik web server itself, and when configured as an IdP, to sign OAuth tokens. Here our journey started with an admin user. An admin can upload and generate certificates. Admin can also download certificates and private keys. So far, all good. At this point, we speculated, can a user download the certificate? So we tried. And whoops, we found that not only a user can download it, no authorization is required at all. So anyone can download the private key. But we do have a limitation here. The internal UUID set by the Authentik server is required for this request. So, a private key can be leaked. Should we care? An attacker possessing the private key can impersonate the Authentik server itself, and by that phishing users or admins, and also he can impersonate tokens, users' tokens, and by that getting access to any system trusting Authentik. So with our motivation set, we were thinking, how hard can it be to leak a UUID? This question took us into a rabbit hole. At this part of the research, we already knew there are many API endpoints and paths, and we noticed that some API calls are leaking some internal UUIDs. So we speculated there must be one API in which we could leak this data. We were looking for direct leaks from the API itself. We requested each API in the specification, but this attempt failed. Then we encountered an excellent article by Eltam. Defined a new class of vulnerability, namely ORM Leaks. This article is about insecure use of ORMs can leak into information leaks. These techniques allows attacker to leak data like SQL injections but provided by the ORM. So, the pattern we are looking for, if we want to find ORM leaks, is using the filter method within the unpacking operator, the double asterisk, apply to user supply data, allowing us to leak some internal data and hopefully our UUID. So, after some time, we found a promising instance, the Events Log API. In the Events API, we found that this API can be accessed by any user of the system. So we found some random API. What is it about anyway? This API returns timestamps and values. Each value represents the number of occurrences of the log in the time slot. It is used by the Authentik UI to show event hits in the event menu. So, we have an event log leak. Is it relevant for us? While inspecting the event log, we found the following entry. When admin uploads the certificate UUID is logged in the event log. Notice that the key data is masked here. So, here's a typical API request to this API. If a log entry is found, a non-zero value is returned. We updated the request to include a regex query to exploit the ORM leak. When using this regex request, notice the response. If it includes a number different than 0, then we found a log entry. With this API behavior, we have an oracle. Let's look at the demo. Using this oracle, we were able to leak each next character from the API, and eventually the full UID and the private key. After exploiting this issue and creating a POC, we tried to use a normal user's permission, but this attempt failed. We found that permissions are required in the database itself. So, to summarize this part, we reported the issue to Authentik security team, they confirmed it, assigned a CVE, and fixed it. And now, as promised, Authentik privilege escalation. Here our journey started as a non-admin user. We logged in as non-admin user. Then we encountered an interesting functionality. A user can create an API token for himself. He can use it to access the API. We created a token, and then we noticed that a token has an expiration date. A user can copy the API token, and the user can edit his token. Edit means update. A user can modify the token description, and by default, the expiration date is updated. So, we decided to inspect the token update request. When updating the token, we noticed that an interesting JSON key in the response, the user object. That led us thinking, what if we try to update the user? So we added the user and set the value to 6. This request returned a valid response, and the user key is updated. Let's look at the demo. We logged in as a normal user. we copy his cookies so we can make API calls to the Authentik server. Now using this, we requested the token, and we get the API token. This is the token content. Using this, we verify that it's working, the token itself, and it's working. Now we change the method to put, and we updated the token. We add the user token, the user attribute, and set it to 6. And we got a valid response, and it seems like the user is updated. Let's verify that the token is still valid, and it seems like it is valid. So we use a minor API, set password, and let's see if it works. We try to log in with the user that is provided by the API, and the password that the attacker set. And we have admin access to the system. Okay. So we have admin API key. We got full control of the system. To summarize this part, we reported this issue to the Authentik security team. They confirmed it, assigned CV, and fixed it. Let's conclude our session. In part 1, we covered Keycloak research and web race conditions. We started with the technical background, and then, In part 1, we covered our Keycloak research. We started with a technical background and got into web race conditions and the single packet attack and HTTP version 2. Then we evaluated our Keycloak, our alert techniques, and showed the demo. In the second part, we covered Authentik research. We started with the technical background on ORMs, then covered the private key, info leak, and ORM leaks. Then we concluded with our Authentik privilege escalation. Research takeaways. HTTP request processing isn't atomic. HTTP version 2 using streams. The single packet attack can be used to test web applications for race conditions. For developers, ensure endpoints make state changes atomic. Double check access to restrictions on sensitive endpoints, like certificates. Avoid direct manipulation on tokens. And when using ORMs, be aware of vulnerable patterns and safe use. These are the references. Oh, one more thing. In Authentik, with an admin privileges, we found an interesting functionality. Built-in impersonation. This functionality allows an admin to log in as any user on the system. So, your identity is mine, or any authenticated user from the system. Questions?
Yeah. So do we have any questions? We have like a few minutes left, so we can go with it. Anyone? Yeah.
Hi, this is Fahad. Did you done any OAuth-based identity validation apart from API?
Sorry, I didn't get the question.
Sorry. For these two IdP, did you done any validation about OAuth-based other than API token, basic bearer token?
I'm sorry, I'm not getting the question.
Yeah, open authentication I'm talking.
Oh, okay, OpenID?
Yeah. For these two IDP, did you tested open authentication?
Did I test OIDC in these systems? No, I didn't.
Yeah. Any other IDP did you researches recently? Same, other than open source?
No, not really.
Sure. Thank you.
Do we have any more questions? Yeah.
Right. The research is great, but then it's throwing up more questions. So one is actually that not always the private key is used as the authentication, and second thing is how much is the success, right, to get the private key of the web server through the API? It's a vulnerability, or is it always possible to use race condition, and how do we prevent it?
So if I get it right, regarding race conditions, if you want to prevent it, as I saw the first example, I didn't manage to exploit the race condition because of transactions in the application. So there's a database mechanism you can use to prevent race conditions for critical sections in the code that you need. And regarding the first one, it was about certificates, but I can't. Can you ask it again?
Yeah, what I meant to say is, this is only one of the condition where you could find get the private key using the vulnerable API, or is it is it a common thing that you use the vulnerable API across any application to get the private key?
Is it common thing? No, it shouldn't. Private key shouldn't be public, never should be public, right? So yeah. Any other questions? Okay, thank you for attending my session. For more info, check out my research blog posts. For any feedback or questions, you can contact me later or via LinkedIn. Thank you very much.